Assalamu alaikum. Hope you are doing fine. One of the important applications of Kirchhoffs rules is Wheatstones Bridge. It is used to compare the resistance in a network, and it is also used to find the unknown resistance in a given electrical circuit. In this video, we are going to learn about Wheatstones Bridge with the help of a few experiments. The circuit that you see here is nothing but Wheatstones Bridge. To make this, I have used 4 resistors, each one of them of 1 kilo ohm resistance. These 2 junctions are connected to a battery. This is the positive terminal and this is the negative terminal of the battery. And at these 2 ends will be connected to a galvanometer. I connect this end to and this end of the Wheatstone bridge is connected to another end of the galvanometer, something like this. I will repeat the connection that I have made here. These 2 junctions of Wheatstone bridge is connected to a battery, and these 2 junctions of Wheatstone bridge is connected to a galvanometer. This is a moving coil galvanometer. Now I will turn on this battery. You may find a slight jerk in this. Now the galvanometer reads 0. This means the electric potential at this point and also at this point is same. We know when the electric potential at 2 points are same, no current flows. That is why when I have connected this galvanometer to these 2 points, no current is flowing through it. So it shows 0 deflection. We call this point as null deflection. And this is the condition for the balancing of a Wheatstone bridge. Now, with the help of a multimeter, I will measure the voltage, that is a potential, electric potential at these 2 points. I have set the multimeter to read the voltage. I place this red probe here and the black probe is placed to the negative terminal, which is nothing but this. This is the negative terminal of the battery. Now it reads a 2.41 volt. Now I keep this point as such. Now I am going to measure the voltage at this junction. See, it is again 2.41 volt. This confirms that these 2 junctions are at same voltage. That is why no current flows through the galvanometer and it reads 0. Now I am going to break this balanced condition of the Wheatstone bridge. For that I am going to replace any one of these resistors with a resistor whose value is different. The resistor that I have used here have 1 kilo ohm resistor. All the 4 resistors are of same value. That is why these limbs have same current and the voltage at these 2 points is same, so no current flows. Now I will remove this and replace this 1 kilo ohm resistor with the 100 ohm resistor. You see, before doing so, I turn off the battery. Now I desoliderize it. I'm going to desolder this first. I desoldered this 1 Coulomb resistor. I place some paste for soldering. Then, the help of soldering iron, I am going to solder this 100 ohm resistor to this end. I will do the same thing to this end as well. Now, I have replaced this 1 Coulomb resistor with the 100 ohm resistor. Now, the potential at these 2 points will not be the same. Now, I will turn on the battery and see what happened to this. Earlier, when the bridge was balanced, it was showing 0. Now see, I turn on this. You have observed, now it is not reading 0. It has moved towards one side. It is for the reason that these 2 points are at different potentials. So current is flowing through this galvanometer. So it shows some value, some deflection. Now I am going to measure the voltage at these 2 points. Place the red probe here with respect to this point. This reads 0.9 volt. The voltage at this junction is 0.9 volt, and I will measure the voltage at this point. It is 0.7 volt. So this shows that these 2 points are at a different potential. So there is a potential difference between these 2 points. So current is flowing through this galvanometer. Wheatstones bridge is used to compare 2 resistance given in a circuit. They can also be used to find the resistance of unknown resistance. Let's move ahead. A Wheatstones bridge comprises of 4 resistors PQ, R and S, connected in this manner. Here, between junction B and D, a galvanometer is connected, and a cell that provides EMF Xi is connected between junction A and C. We know current always flow from positive terminal of cell towards the negative terminal. So the current supplied by this cell is nothing but I, which flows from the positive terminal of this cell towards the junction A, and it moves towards B. Then from there it reaches C. Then from C it ends at the negative terminal. This is how it completes the path. This is one path of the current. After reaching point A, suppose if it moves through R, then it takes the name I2, reaches D. From there it moves to point C through resistor S. This time we denote it by letter I4. The current is denoted as I4. After reaching C, it flows, it takes this path and reaches the negative terminal. This is how it starts from positive terminal and ends at a negative terminal. Now, that's all about the direction in which current can flow in this circuit. That is through Wheatstones bridge. Now, I am going to apply Kirchhoffs' first rule and the second rule to get the final expression for Wheatstones Bridge. Let's do it. I will apply Kirchhoff's current rule to junction B. Apply Kirchhoff's current rule to junction B. If I do so, what do I get? We know Kirchhoff's current rule says that sum of current meeting at a junction is 0. So the current which moves towards B is always taken positive according to Kirchhoff's current rule that we have learned in the previous video. Here I1 is taken positive because it moves towards the junction. Then from junction B, another current moves, that is the Ig. So I take it as negative minus Ig because it moves away from the junction. Then there is one more current which moves away from the junction B. There is nothing but I3. As it moves away, again we take it as negative minus I3. Sum of these three currents is 0 according to Kirchhoff's current law. I take this equation as equation number 1. Now I am going to apply Kirchhoff's current rule to junction D. Apply Kirchhoff's current rule to junction D. If I do so, at junction D, three currents meet at junction D, which is I2, I4 and Ig, which is flowing through galvanometer G. Here, galvanometer have resistance G and the current flowing through this is nothing but Ig, represented by letter Ig. So, current towards D is I2. So, I2 is taken as positive. Then, another current which is moving towards D is Ig. It's also taken as positive. Now, I4 moving away from D, so it is taken as negative. Minus I4 equals to 0. According to Kirchhoff's current rule. I take this equation as equation number 2. Now I will apply Kirchhoff's voltage rule to loop AB DA. Apply Kirchhoff's voltage rule to loop A B D A. As we have studied, Kirchhoff's voltage rule is applied to a closed loop. Now let me do it. And it says that sum of product of current and resistance in a closed loop is equal to the total EMF in that loop. Let's find out that. Then I start from A. Here the current flowing through resistance P is I1. I multiply this current with the resistance P. Then I add this. Then I reach point B. From here, the current Ig is flowing, which are passed through galvanometer of resistance capital G. Then it reaches the point D. So I add and I move towards A to complete the loop. Here the current in this part of the loop is I2. Here I2 is flowing in the opposite direction. If I want to complete this loop, I have to move from D towards A. But the current is moving in the opposite direction. So, in the place of plus, I have to mention minus here. According to Kirchhoffs voltage rule, I2 and is multiplied with the resistance, is nothing but R. So the sum of these three is equal to total EMF. If you look at this carefully, you will find that this loop do not have any cell. So the total EMF in this part of the circuit is 0. So I take this equation as equation number 3. Now again I will apply a Kirchhoffs voltage rule to this loop A, B, C, D, A. Let's do it. Applying Kirchhoffs voltage rule to loop A, B, C, D, A. If I do so, I'll start from here in a similar way. I1 flowing through resistance P plus I3 flowing through Q. Then here at the point C to D I have to move. Current flows in the opposite direction. So I write the minus sign here. Then I4 is flowing through resistance S. Then after reaching D, from D to complete the loop, I have to move towards A. So what happened here? The current is flowing in the opposite direction. So minus sign I2 flowing through resistance R. So it is multiplied. It is equal to the total EMF in this loop. We know there is no, that is obvious, there is no cell is present in this loop. So the EMF is 0. It is 0. This is equation number 4. When the point B and D are at the same potential, it means the bridge is at a balanced condition. In such case, usually we know when 2 points are maintained at same potential, then the potential difference between these 2 points is 0. When the potential difference or voltage between 2 points is 0, then there will be no flow of current. Similarly, when B and D are at the same potential, no current flows through G, and we call this condition as null deflection, because galvanometer shows 0 deflection at this point. Here null means 0. So when B and D are at a same potential, current through galvanometer is 0. I just taken as 0. Now I box this. This is the condition for null deflection. I take this as equation number 5. Now I am going to substitute equation number 5 in equations 1, 2 and 3. 5 in 1, 2 and equation number 3. If I do so, 1 will become, here Ig becomes 0. So one becomes Ig, I1 minus 0 minus I3 equals to 0. This can be written as I1. I take I3 that side. Minus I3 becomes plus I3 when taken to another side. Now I take this equation as equation number 6. Now I'll substitute equation 5 in equation number 2. I get I2 plus 0 minus I4 equals to 0. Now I take a minus I4 to the other side. So I get I2 equals to I plus I4. This is taken as equation number 7. Then I will substitute equation number 5 in 3. Here the same thing happened. This term becomes 0 because Ig is 0. When it is multiplied with G, the whole term becomes 0. So what I get? I1 P plus 0 minus I2 R equals to 0. This can be written as I1 P equals to this term taken to another side. So becomes plus I2 R. This is taken as equation number 8. So I have 3 equations. Now I'll substitute the equation 6 and 7 in equation number 4. Substituting 6 and 7 in equation number 4. What I'll get if I do so? In the place of I3, I'll write I1. See, I1, P is kept as such. In the place of I3, I'll write I1. So I1, Q, and in the place of I4, I'll write I2 minus I2, yes, and this term is kept as such. I2 minus I2 R equals to 0. This is a new form of equation number 4 obtained by substituting equation 6 and 7. I numbered this equation as 9, equation number 9. Now, if you look at this, you will find that these two terms have I1 common, and here these two have I2 as common. Now I take common term outside, I get I1 into P plus Q. Then here minus I2 is taken out. Then what I get? S plus R within bracket equal to 0. This can be written as, now if I take this term to the another side, negative minus sign will become plus. So I get this equation I1 P plus Q equals to I2 S plus R. This is equation number 10. I take this equation number 10 for my convenience. This equation number 10. Now here I have an equation which appears somewhat similar to equation number 10. Now if you compare these two, equation 10 and 8, we have I1 on the left hand side, and here I2 in both equations are present on the right hand side. So I am going to divide these two equations. What I will do? Divide equation number 10 by equation 8. If I do so, what do I get? You see, I1 into P plus Q divided by I1 P is equal to the same thing we do on the other side as well. I1 into S plus R divided by the right hand terms of equation 8, I to R. So here similar terms are cancelled. So we get a equation with the remaining terms, something like this: P plus Q upon P is equal to S plus R upon R. This is what remain here. I box this equation. I'm going to expand this equation. Okay, there is no space left here. So I will expand this equation here. See, on expansion, how to expand this? See, here I write that as such: P plus Q upon P equals to S plus R upon R. Yeah, okay. Let me do it. First, I divide this term with a P. P upon P, then plus sign, then Q is divided by P. Then here I do the same thing. See, S upon R plus R upon R. So if I do so, this two get cancelled. And what remains is 1. The same thing, the same thing happened here. 1. It did not get cancelled. Remain as such. Now, when P is divided by P, you get 1. And I write here 1 plus Q upon P beside S upon R plus 1. Now I take this term to the left hand side. So plus 1 becomes minus 1. 1 minus 1 plus Q by P equals to S upon R. Now this will get cancelled. What remains is Q upon P equals to S upon R. Now I take a reciprocal of this. When I take a reciprocal of this term, I get P upon Q. So the same thing I have to do this side as well. S upon R will become R upon S. This is the final equation. I box this. This is known as bridge balance condition. When P upon Q is equal to R upon S, only then galvanometer will show null deflection, zero deflection. And here, if we know P and Q, then remaining two resistance can be compared. We can compare R and S if we know P and Q. If we know three resistance P, Q and R, then the value of S can be obtained. This is how Wheatstones bridge can be used to compare two resistance, and as well it can be used to get the value of unknown resistance. And before coming to conclusion, let me tell you how to find or how to mention the direction of current here. This is a circuit. Now we know current always start from positive terminal of the cell or battery. We'll start from here. After reaching this end, let us move up to point A. Now after hitting point A, now we find the two paths. Current can flow through R or it can move through P. Suppose I choose this path. So the current moves this way. After reaching B, again it finds two paths. It can flow through galvanometer or it can pass through resistance Q. Now I choose this path. So it moves, which is C. Now from C, the shortest path found by the current to complete the circuit is this path. So from there it reaches the negative terminal. This is how it completes a loop or circuit here. So suppose after reaching this end E, the current has chosen this path. Now then start from here. This point A. So from there it starts moving in this direction. It is D. After reaching D, it will flow through S. See, this is the direction. Then after reaching C, it will choose this path. It will move towards the negative terminal of the cell. This is how, see, start from here. That is why I flows in this direction. Then through R, I2 flows in this way. And through S, the direction of a current is represented this manner. And I here from C to negative terminal is represented this manner. Whereas here, in case of this line, if you start from here after reaching A, so is the direction of current. It moves towards B through P. So direction of current is represented this manner. Then from B to C, this is the direction of current. Then from C to negative terminal, current takes this path. Suppose there is one more possibility here. What is that? If a current has chosen this path after reaching the B, we'll start from here. Chooses this path. Now instead of moving to point C, if it decides to flow through G, then takes this path. This is how we get the direction of IG. After reaching D, it will flow in this manner through S. So this gives the direction of I4. After reaching C, this is the shortest path found by the current to reach negative terminal. This is how it completes the path. Starts from positive terminal and ends at the negative terminal. This is how you can easily mention the direction of current in this circuit without by hearting them. I hope this video is useful. If you have any kind of doubt related to the topic, kindly put your questions in the comment section. Thanks for watching.